In this episode, the world's largest cruise ships.
The Oasis class of ships is in a class of its own. Nothing comes even close in terms of size.
A nautical venture on an epic scale.
We have 6 engines and the total output equals to power of 1,200 road cars.
And the pioneering historic innovations.
They're amazing. Very, very impressive.
So it's reached its full efficiency now, and unfortunately, the paddle wheel just can't keep up.
That made the impossible possible. In 2009, history was made with the launch of the largest class of passenger ships on the planet. Royal Caribbean's Oasis-class cruise ships take maritime engineering to an unprecedented level. Now, in a shipyard in France, a third Oasis-class vessel is under construction, and when complete, will be the biggest of the group. Longer, wider, and heavier than any passenger ship that has come before. For the project's director, Petteri Kaiso, it's an almighty engineering challenge.
The amount of technology, engineering and design that has been put into this ship class is quite extraordinary. It's simply mind-boggling. Nothing like the Oasis class of ships has been built before. This is in a class of its own. The complexity of it is really staggering.
And for Timo Ijuri-Javori, one of 2,500 people working on the new ship, the scale never fails to amaze.
Sitting next to her makes me feel like standing next to a skyscraper.
When complete, Harmony of the Seas will be almost 8 times longer than the Statue of Liberty is high, taller than 14 double-decker buses, and twice as heavy as the world's largest aircraft carrier.
She's about 360 meters long. The funnel is reaching a height of 65 meters from the water level, and her gross tonnage is 227,000 tons. She is the largest ship ever built.
Construction on such an immense scale would be impossible without a pioneering innovator from the past. The art of staying afloat has fascinated man for thousands of years.
Thank you.
The ancient Egyptians built vessels from reeds, perfect for cruising the Nile.
Oh, hello.
But their absorbent nature meant they weren't built to last. For centuries, wood was the material of choice.
Onward.
But warfare led to the use of metals and the mighty ironclads.
Fire.
Although iron could be brittle and prone to rust.
Oh, dear.
And as mariners strived to build bigger, they needed a stronger and more resilient solution. The answer would lie in a material that revolutionized the modern world.
In the chamber behind me, there's about 150 tons of liquid molten steel. The temperature is phenomenal. It's about 1,650 degrees Celsius.
Engineer Rhys Morgan is in the north of England, in the extreme environment of a state-of-the-art steel plant in Sheffield.
This is absolutely amazing. It's the best thing I've ever seen.
Different grades of steel are made by alloying iron with various metals and elements.
Oh my God! The crucial starting point of the steel-making process is to remove the carbon and the other impurities. And now it's being poured into the ladle, and it'll go to the next stage, which is to take it to the converter.
During this second process, the steel is further modified by adding extra alloys and blowing in oxygen.
What's going on here is the very basics of steel making. And this wouldn't have been possible today without the pioneering work of one engineer that's known throughout the world by all material scientists.
In the mid-1800s, British inventor Henry Bessemer revolutionized what had been for centuries an incredibly specialized and lengthy process.
Traditionally, the wrought iron was layered with charcoal and heated over days, and the charcoal would diffuse into the iron, and that would produce the steel qualities. Very complex and difficult to achieve, and therefore very expensive historically.
But Bessemer had a solution that would make steel a viable proposition for mass production.
And this is it, the Bessemer converter. It's a huge, vast cylindrical chamber, about 6 meters high, and it would have held 25 tons of steel.
The converter's capacity may be impressive, but the contraption's real ingenuity was the speed at which it could create steel. Bessemer discovered that pumping air into the iron accelerated combustion, increasing carbon reduction and burning off impurities quicker, resulting in quality steel in a fraction of the time.
To show how oxygen injection really increases the combustion process, I've got a simple demonstration here. I've got a tray of charcoal. With my thermal camera, I can see the temperature of these coals at the moment. It's around about 450 degrees C. So now what I'm going to do is start to blow pure oxygen onto these coals and see the effect. Wow, look at that. The impact is amazingly impressive. So if I now look at the temperature, it's gone up to 1,000 degrees C, a hugely dramatic increase in the temperature of these coals. So Bessemer had found a really amazing process to reduce the carbon in steel.
As mass production took off, steel's elasticity and strength proved a perfect match for the railways and the world of shipping. At the height of its demand, 10,000 tons of Bessemer steel was produced each week in Sheffield alone.
And although processes have become more sophisticated and complex, it was thanks to the engineering genius of Sir Henry Bessemer and his revolutionary machine that over 1.5 billion tons of steel are now produced annually right across the globe.
Measuring 362 meters long and weighing 227,000 tons, the Harmony of the Seas needs a very special method of construction and assembly.
Harmony of the Seas requires approximately 50,000 tons of steel.
And the shipyard have a production line of Goliath proportions to process it. Vast steel sheets are brought into the plant by rail. There, automated systems cut the sheets into thousands of individual components.
Here we have one of the pieces. This is normal strength steel, a very typical piece. Thousands and thousands of pieces like this on board.
The steel panels, girders and smaller components are then welded into modular sections called blocks.
After the panels have been fitted with stiffeners, we start directing the bulkheads onto the panel. And at this stage we start calling it actually a block. This is typically a 1 deck high block of steel which has the deck, the bulkheads, the pillars, everything it needs to form one deck of the ship. The block, as you can see now, it's turned upside down. So actually we're looking at the ceiling of any given deck. And the reason why it's like this is of course that it's much easier to weld everything when it's in this position instead of welding in the ceiling. And once the outfitting is mostly completed, then it's turned upside down, or the right way actually, and then you start building blocks on top of that.
The individual sections are then joined together to form what are called grand blocks, 90 in total.
Here we have one of the grand blocks, one of the 90 grand blocks. And this is actually consisting of 5 decks. It's one of the highest grand blocks we have. So for this you need probably around 10 blocks to make this one big grand block.
A custom-built, super strong gantry crane then lifts each grand block into the dry dock.
A grand block, when the crane lifted it up, it can weigh up to 1,100, 1,200 tons. And that is of course quite a massive load.
All 90 blocks are assembled to form the record-breaking ships.
It actually could be compared, and this is of course simplifying it a lot, but you can compare it to building a Lego structure actually.
But the Oasis-class cruise ships are no toy, and its designers and engineers will have to push the boundaries, drawing on the great pioneers of the past.
You can feel the vibration, and then you see slowly movement.
To create this record-breaking fleet of impossible engineering. A team of nautical designers and engineers have set themselves an extraordinary challenge: to build a fleet of cruise ships larger than anything ever seen before. The Oasis class of ships dwarfs its predecessors. And in a shipyard in France, the third of the group is almost complete. When launched, the Harmony of the Seas will become the biggest passenger ship of all time.
You can definitely call this ship a small city. It can house almost 9,000 passengers and crew on board. It's a fully self-sufficient island, if you will.
But these ships' dozens of restaurants, theatres, bars and attractions would all be impossible without one vital component, buried deep within their interior.
The engines are the heart of the ship, and the electrical network is the veins to provide the power forward to the ship. Without the engine, the ship is not alive.
So how do you create an engine powerful enough to move a floating city across the oceans and provide enough electrical juice to keep more than 6,000 passengers and over 2,000 crew comfortable and entertained? It's a problem that would have been unachievable without one of history's great innovators. The Industrial Revolution gave birth to the steam-powered engine. Although it increased productivity, it came with a very big problem. To get rid of their bulbous boilers, engineers broke the mold, burning fuel within a new engine. Compressing gasoline and air and igniting it with a spark plug to drive the piston. The internal combustion engine was an industrial game changer. But as the 19th century drew to a close, another innovation was just around the corner. Mechanical engineer Henrik Birgo has come to Copenhagen in Denmark, a capital city which owes a debt of gratitude to a piece of engineering genius. Inspired by a truly remarkable innovator, Rudolf Diesel.
This is the H.C. Ørsted power station in Copenhagen. And inside, you'll find a giant version of Mr. Diesel's early engine concept, which changed the face of the industry globally.
As it powered up in 1933, the diesel-powered H.C. Ørsted was the largest engine of its kind, measuring an impressive 12 meters in height and weighing 1,400 tons. Still in working condition, in its heyday, it produced a mind-blowing 15 megawatts of power.
It's absolutely huge. Standing next to this 3-4-story tall engine is very impressive.
But despite its supersized stature, the real power from this engineering colossus is drawn from Rudolf Diesel's brilliant design, patented in 1894.
It's very hard to believe that the inspiration to this piece of engineering came from an object which actually fits into the palm of your hand.
Although the internal combustion engine had made a huge global impact, Rudolf Diesel's design innovation made it even more efficient. Crucially, it didn't require a spark plug, using only compression to ignite the fuel thanks to its innovative double-acting piston.
This is a fire piston, and this little piece of kit was what inspired Rudolf Diesel in his development of the diesel engine. And it works like this. You have a small cylinder where you add a bit of cotton wool. The cotton wool will work as fuel. You have a little piston. When you push down the piston here, the air will be compressed. The temperature will increase and it will finally ignite the cotton wool. And it goes something like this. Compressing the air created heat. The heat forced the cotton wool to burn, turning it into energy, which forced the piston back up again.
The perpetual motion within the compression ignition engine worked in almost exactly the same way. Air is drawn into the piston and rapidly compressed, creating heat. Named after its inventor, high-energy diesel fuel is then added, causing combustion, which pushes the piston out to start the process once more. Unlike the spark ignition engines, it was the continual firing of this diesel-fueled piston that created superior power and efficiency.
This means that you're able to burn not only many different fuels, but also cheaper fuels compared to a spark plug engine concept.
When this ingenious piece of engineering was supersized, it created the awe-inspiring H.C. Orsted engine, which incredibly can still come to life more than 80 years after it was first fired up.
We're now about to ask Otto to start up the engine which was once the largest one in the world. You can feel the vibration and then you see slowly movement. Very, very impressive.
The 8 giant cylinders would throw out more than 22,000 horsepower, operating at around 75% efficiency, compared to as little as 10% achieved by steam engines.
Basically, what you see here haven't changed dramatically in almost 100 years.
Diesel's innovation was so remarkable, it transformed the industrial world. But its superior power and fuel efficiency had also made a huge impact in the world of shipping. The launch of the first diesel-powered liner in 1912 would transform the maritime world. Cleaner and more compact than its steam-driven predecessor, its engine was also up to 3 times more efficient, increasing range and opening up a new raft of trade and travel possibilities.
I would say within mechanical engineering, it's the most important leap, no doubt of that.
The H.C. Orsted in Denmark might be a monster, but the power of each Oasis-class ship is 6 times greater. The huge vessels use 6 Wärtsilä diesel engines, the largest of which is almost 13 meters long and weighing well over 200 tons. Fitting them is an engineering feat in its own right. Now, 2 years into this trailblazing project, what was once an impossible dream is finally becoming a reality for engineer Timo Iyuri-Javori.
We are now on the main engine room of the ship, and we are going to test diesel number 1. So this baby here. This is one of the most exciting days of the project. Yo, Ivo, let's start her up.
The giant engines generate electricity that not only powers the motors that drives the 227,000-ton ship across the world's oceans, but also provides enough energy for the floating city above.
It feels great to see the engine alive. In total we have 6 engines, and the total output of the ship is 93 megawatts. That equals to a power of 1,200 road cars.
Without this mighty powerhouse, the world's largest cruise liners would be an impossible dream.
Starting of the main engine is one of the main milestones on the shipbuilding project.
But to complete this structural masterpiece, engineers face more challenges and will have to turn to another of history's great innovations
The paddle wheel's got quite a good acceleration straight from the start.
to produce more impossible engineering. In a shipyard in France, the third of the largest class of cruise ships ever built is nearing completion. When launched, the Harmony of the Seas will be a record breaker in its own right.
It is 361 meters long, 47 meters wide on the waterline. We have over 2,700 passenger staterooms, and we can have almost 9,000 people on board at any given time. Largest cruise ship in the world, pretty impressive.
The enormous scale and width of the vessels has allowed them to do something never before attempted on cruise ships. The Oasis class has a split superstructure, which allows open space through the middle of the ships.
Now we are on deck 8, forward, facing backwards. We are on the Central Park area, one of my favorite places of the whole ship. The inside cabins are not anymore inside cabins, but we have a perfect view to the park. We will have solid pavement here, live planters, just like a normal park. This concept is totally unique. You cannot find it anywhere else. Only an Oasis class has this split superstructure.
Its upper structure may be impressive, but for the ship to be a viable design, it will also have to deliver beneath the waves.
So there are a few factors that are very important for the fuel efficiency of the ship. And clearly the biggest one is the hull shape. The hull shape needs to be extremely well designed so that you have a good hydrodynamic shape.
So how do you engineer a streamlined shape to efficiently power this gigantic ship through the world's oceans? Achieving this may not have been possible without an innovative breakthrough from over 150 years ago. Dr. Andrew Steele is in the British seaside town of Torquay, a top venue for one of the most extreme forms of nautical competition.
This is a Phantom 19 offshore circuit racing class powerboat, and it's built for one thing: speed. The shape of the hull has been precisely matched to the power of the engine, and that means that this thing can cut through the water at incredible speeds, in excess of 100 kilometers an hour. This really is incredibly exciting. The ability of this boat to cut through the water would not be possible without the pioneering work of one man here in the seaside town of Torquay.
Over 200 years ago, the advent of engines transformed the maritime world. But naval designers still needed a greater understanding of how their ships moved through the water, so they could install enough power.
For centuries, shipbuilders had a kind of one-size-fits-all notion about ship hulls. There was one generic shape that was considered the most efficient, but there was no real way of testing this, of working out how much drag, how much resistance a hull would encounter as it moved through the water.
In 1870, engineer William Froude tackled this problem, building a groundbreaking facility that would set the benchmark for hydrodynamic testing to this day.
It was here at his home in Torquay that Froude built the world's first tow tank.
The 76-metre-long water tank allowed Froude to carry out precise tests at consistent speeds. Handcrafted models were mounted on a carriage and dragged through the water on a steam-driven pulley, enabling Froude to make his hydrodynamic calculations.
Froude's original tank out there in the garden is sadly no longer in existence, but we do have this lovely swimming pool. And here we're going to try to explain Froude's revolutionary discovery and how it changed the world of shipping forever. We've got three different shaped hulls: a flat-faced square box, a slightly streamlined rubber duck, and then this sleek speedboat.
After ensuring they are equally weighted, each object is towed by a rope attached to a scale, measuring the amount of hydrodynamic drag.
You can see this isn't slicing through the water, it's sort of making a load of turbulence. If you look at the scales, 3, maybe even 4 kilos. That's a lot of drag, a lot of resistance.
Next up, the slightly more streamlined rubber duck.
Well, that feels much lighter, and the scales bear that out. Maybe 1.5, 2 kilos of force there. And you can see the pool much less disturbed. There are far fewer of those eddies. The duck's just skimming across the top of the water. But I still think we can do better. Let's try the powerboat. And this is almost effortless, maybe 600 or 700 grams tops. You can see much less disturbance to the water. The pool's almost still. And even from this scale model, you can see why we make boats in this streamlined shape.
Although Froude appreciated the importance of friction between hull and water, his real breakthrough was understanding the drag illustrated by the model's wake pattern.
Froude's real eureka moment was when he realised that he could use a law to relate the drag on a scale model of a boat to one that was full size.
His ingenious formula created what has become known as the Froude number.
That Froude number can then be used to compare a model ship to a full-size one. By making sure they've got the same Froude number, you can work out how much drag the larger ship will experience, work out how big an engine you need to install, and it was this discovery that revolutionised hydrodynamics and the shipbuilding industry.
During the 1870s, Froude's groundbreaking innovation was home to over 46,000 experiments. His pioneering work paved the way for hundreds of state-of-the-art tanks in existence today, many of which have been christened with water from Froude's original tank. Engineers of the Oasis-class ships used huge 10-metre-long models in a tow tank that simulated a variety of sea and weather conditions. The result? A super-efficient bulbous bow design that has been further enhanced by a cutting-edge system known as air lubrication.
The air lubrication technology requires microbubbles, so we push the air through the bottom of the ship through a specifically designed grid that creates the microbubbles. We have them in a few locations on the ship in the forward part, and as the ship moves forward, the cushion of air moves along the ship's hull.
The velocity and size of these microbubbles orientates the airstream along the underside of the vessel. The resulting cushioning effect significantly reduces friction and the power needed to propel the ship, increasing energy efficiency by around 5%. This colossal class of cruise ship may be streamlined under the surface, but above water, their sheer stature poses a huge challenge.
As we have such a big wind profile on the ship, it's almost like driving a skyscraper at the seas. We have to be able to control her to the direct position what we want to have to be.
So how do you provide enough power, control and efficiency to maneuver such a huge vessel so it can cope with weather conditions and cruise long distances? The solution to this seemingly impossible conundrum came about over 180 years ago. Naval architect Lucy Collins is in Dartmouth on the English coast, on board a boat equipped with an innovation that dominated shipping in the 19th century.
And this is it, the paddle wheel. Once the steam engine came along, the paddle steamer was born, and it was unrivaled as the main form of ship propulsion across rivers and the seas.
During the early 1800s, paddle-driven ships such as the SS Savannah could cross the Atlantic. But as impressive as the technology was, it wasn't efficient.
So the paddles are on the side of the ship, and as it goes over waves, and particularly in rough weather, the paddles are going to start coming out of the water on either side, and this is going to reduce efficiency and speed.
Paddle steamers had dominated the seas for decades, but engineers were now looking for a viable alternative. Their inspiration came from an ancient invention.
For most of those early innovators, the focus of their attention was this, the Archimedes screw.
Dating back to the 3rd century BC, this crank-operated contraption was traditionally used to transfer low-lying water into irrigation ditches.
So we can see if we turn the drill on, we start to get water transferring up the pipe and then overspilling at the end of the pipe. So inventors realised that they could apply this to a ship. If you put the screw surface on the ship, it can push the ship through the water.
In 1836, engineer Francis Smith patented a revolving screw to power a 6-ton motor launch. But having snapped the metre-long section during testing, he realised that the remaining fragment drastically increased the boat's speed. What he had happened upon was a precursor to the modern-day propeller. Despite his discovery, the Navy was convinced that paddle power was still the future.
Adamant about the advantages of his design, Smith decided he needed to prove his doubters wrong. He decided to pit his screw-driven SS Rattler ship against the paddle-driven SS Electro in a tug-of-war and a race.
With both ships equally weighted and equipped with identical engines, Smith's lifelong work was on the line. Today, Lucy is recreating this famous event, taking on a propeller-powered bike in her own paddle-powered vessel.
So the paddle wheel's got quite a good acceleration straight from the start. But it seems like the propeller blade is just reaching its full efficiency. And unfortunately, the paddle wheel just can't keep up. The paddle wheels are slipping, and it seems like the race is lost.
As Smith's screw-driven vessel blew its paddle-powered opposition out of the water, a new chapter in propulsion had begun.
That was the start of the propeller being the primary means of propulsion for ships, from then until now, almost 180 years later.
In order to drive the largest cruise ships in the world through the water, the propellers on the Oasis-class vessels are on a predictably grand scale. Each of the 3 bronze screws is 6 meters wide. and weighs 40 tons. But creating a 21st century megaship also requires new challenges that need cutting-edge propulsion solutions.
The ports we sail into are sometimes fairly small, so we want to be sure that we can always maneuver the ship in a very safe way. So we're not dependent on tugs. We can independently maneuver the ship into the ports we want to sail into. We have to really park it on a dime.
The solution lies with an invention developed in the 1950s by German engineer Joseph Becker, who devised a way of doing without a traditional ship's rudder. Instead, he designed something called the rudder propeller, a propeller that could turn through 360 degrees and so steer the ship as well as propel it. The modern incarnation of Becker's concept is what enables the world's largest cruise ships to achieve the seemingly impossible: the podded propulsion system.
We have 3 Azipods, each of them are 20 megawatts in size. And 20 megawatts you could translate to being about 200 family cars. It's a huge amount of power, but considering the size of the ship, it's what we need.
The 3 pods actually act like airplane propellers, pulling the ship through the water, rather than traditional pushing-style ship propellers. Combined with 4 times 5,500 kilowatt bow thrusters, they allow the cruise ship's captains unparalleled control. Dials on the bridge allow the pods to be turned to the desired position in an instant and maneuver the vessels into locations that would have once been impossible.
Well, the Azipods came as a result of really thinking outside of the box. It's ingenious.
But to truly make their mark in maritime history, designers will need to turn to yet another great innovation of the past.
This is a gyroscope, and to explain how it works, we're going to need one of these.
To produce more impossible engineering. The biggest cruise ship on the planet is just 4 months away from completion and launch. The Harmony of the Seas is the latest in a class of ships that eclipses anything that has gone before. Sitting as tall as Tower Bridge, as long as 5 jumbo jets, and as wide as a football pitch. For the project director, Petteri Kaiso, it's a dream job.
When I really look at her, I'm amazed always, every single time by the size of the ship. It's big, but it's beautiful, it's awesome.
This mind-boggling structure will hold up to 6,000 guests, making customer satisfaction the #1 priority. A potential challenge when the weather doesn't cooperate.
The clearest issue we have is that the ship is not stationary. It moves, it rolls, it heaves, there's all kinds of movements and acceleration on the ship, which makes it a little bit more complicated.
So how do you keep such an immense vessel steady, so customers and crew can experience a smooth ride, whatever the sea throws at them? Dr. Andrew Steele is finding out how the seemingly magical properties of a classic child's toy provide the solution.
This is a gyroscope, and to explain how it works, we're going to need one of these.
A motorcycle's wheels do more than just power and steer it.
A gyroscope works by conservation of angular momentum, which means that when it's spinning around very, very quickly, it doesn't want to change the direction of that spin. And this can give some pretty counterintuitive effects.
These physical reactions can be extraordinary. An effect known as ghost riding can occur when a bike crashes and loses its rider, but then rights itself and continues its journey. This phenomenal sight is down to gyroscopic forces, such as gyroscopic precession, acting on the bike to try to maintain its original orientation. So how does it work?
Well, I'm going to try and show you with this piece of apparatus here. What we've got is an ordinary bike wheel, but we've filled the inner tube with concrete just to make sure it's nice and heavy. So currently this thing isn't spinning, and that means it hasn't got any angular momentum. And that means it's pretty easy just to make it spin around. It's not very stable. However, if we get this electric drill, we can get the bike wheel spinning. And as we add more speed with the drill, we're increasing that angular momentum. Now it's moving very fast, and now if I give it a whack, you can see this thing is stabilized.
And that's why, in extreme circumstances, a wheel can refuse to lie down. Astonishing as this is, it was the stabilizing effect of the gyroscope that maritime engineers were interested in.
If I get it spinning nice and quickly, I can just balance the spinning wheel on my hand.
Just like a spinning top stays upright, perhaps gyroscopes could do the same for a ship. In 1917, American inventor Elmer Sperry used the effect for the very first time in a large vessel. He equipped the USS Henderson with two enormous gyro wheels weighing 60 tons. Inside, 3-meter flywheels spun at an incredible 1,100 revs per minute, creating huge amounts of angular momentum in order to minimize the ship's roll. Although a huge engineering breakthrough, his brute force approach ultimately proved impractical. And as technology has developed, so has the use of the gyroscope.
Over the years, pioneering scientists and engineers have experimented with these gyroscopic forces to the point where nowadays we can fit tiny gyroscopes on the surface of a computer chip like this one. And they're used everywhere, from mobile phones to aircraft and even ships.
The Oasis-class vessels take the magic of the gyroscope into the 21st century. Instead of the giant spinning wheels employed in the USS Henderson, Harmony of the Seas and her sister ships use a small gyroscope as a sensor, which, via computer, controls mechanical stabilizers.
So in rough seas, what we can use to minimize the roll and the movements of the ship are stabilizer fins. And they are actually fins that emerge laterally from the ship's hull. This is the location we are in now. And what it does, it's sort of like a wing that comes out of the ship. It emerges laterally like this, and then it turns around its axis.
A 20-meter squared stabilizer blade is recessed into each side of the vessel amidships. They're deployed as and when the state of the seas demands it.
Stabilizer mostly counteracts the roll, so the sideways movement of the ship. So if the gyroscopes feel that the ship starts moving this way, it asks the fin to exert force so that it counteracts the movement here, so it tries to always right the ship.
It's now more than a century since the first purpose-built cruise ship set sail on the world's oceans. Now, by drawing from the originators of the past,
Standing next to this 3-4-story tall engine is very impressive.
adapting their ideas, honing them, and making trailblazing innovations of their own, the engineers, designers, and workers constructing the Oasis-class cruise ships are making history.
When first these plans were thought of, I'm sure there were a lot of people who thought that we were absolutely nuts. Absolutely crazy to think of even building a ship this large. But you know, we are not afraid to think large, think big, think outside of the box. And that's what you need. You need a little bit crazy thinking at times to really make great things.
They've succeeded in making the impossible possible.
When we started this project more than 2 years ago, we had only design on the paper. But as we now see it, the dream come true, I feel really proud of what we have achieved.